Good morning, everyone. Today, welcome to my presentation titled Annealed Sparsity via Adaptive and Dynamic Shrinking. My name is Zhang from NEC Lab, and this is a joint work with Shandian Zhe and Professor Alan Qi from Purdue, and Chaoran Cheng and Professor Wei from NJIT, my colleagues from NEC Labs, and Professor Jiping Ye from University of Michigan. Okay, here is the outline. The motivation of our work is that the LASSO algorithm is not always consistent. And adaptive LASSO is a very useful framework to improve the convergence property of the model by introducing adaptive regularization weights across different dimensions. However, choosing adaptive weights is still a very challenging problem. In this work, we propose to solve this problem by introducing the idea of annealing in a modified version of adaptive LASSO. It leads to dynamic shrinking process with very interesting shrinking behaviors, and empirical results are quite encouraging in terms of both feature selection and model predictions. Let's get started. As we know, sparse structures are ubiquitous in many areas of data mining. Examples include brain imaging, network inference, gene expression analysis, and so on. L1 regularized the least square, and in particular, the LASSO algorithm is a very powerful tool to uncover relevant features in problems of very high dimensionality. In 2006, Zhou studied the necessary condition for LASSO to be consistent. That is, whether the model will approach the underlying ground truth when the number of samples approaches infinity. Basically, let's partition the features into two parts. One is relevant, and the other part is irrelevant. And the condition says that in order for the LASSO to be consistent, there has to be a sign vector S in which the following inequality is satisfied. Basically, it states that the features, relevant features should have large correlations with each other, and the correlations between relevant and irrelevant features should be small. Obviously, this condition is not always satisfied, and in order to solve this problem, Zhou proposed the adaptive LASSO by imposing a varying strength of regularization on different dimensions. Here, W is the adaptive regularization weight vector. It is of the same dimension as the model coefficient beta, and each dimension in beta is regularized differently with the corresponding entries in W. It has been shown that by choosing the W as the entry-wise inverse of a preliminary estimator, such as the ordinary least square, subject to a power of gamma, the adaptive LASSO is consistent. Besides this oracle property, adaptive LASSO is also quite useful in imposing structured sparsity patterns in multitask learning. This is achieved by sharing regularization for all the same features across different dimensions. This will lead to partial group-wise sparsity as well as within-group sparsity. In comparison, the well-known mixed norm regularization will lead to very strict group-wise sparsity. That means each row in the model coefficient matrix will either be all zeros or all non-zeros. Later, we shall see that this is, might be a too strict an assumption that leads to worse performance. Here, you might probably see that the key to the success of adaptive LASSO is the choice of the adaptive regularization with W. Unfortunately, there's no free lunch, and learning a good W can be as difficult as learning the right model beta. And next, we will propose our solution. We propose to solve the model coefficient beta and the regularization structure W simultaneously in the following constraint formulation. Here, gamma is the power parameter. A very interesting thing is that gamma in our formulation can either be positive or negative. Due to this time limit, I will skip the details. And for convenience, I will assume that gamma is larger than 0 for ease of understanding. The most important modification is the equality norm constraint. That is, we require that entries in W should be positive and sum up to omega. Here, omega controls the global strength of regularization. For example, if omega is large, entries in W will be large, and the actual regularizer, W to the power of negative gamma, will be small, which leads to a dense solution. On the contrary, if omega is small, then the model will be sparse. As a result, omega can be intuitively considered as controlling the temperature of the system. The larger the omega, the denser the system, and the smaller the omega, the sparser the system. To solve this problem, we naturally resort to alternating optimization. Basically, we first fix W and optimize over beta, which gives a standard adaptive lasso. The most interesting part is actually the second subproblem. That is, when we fix beta and try to optimize over W. Here, we rewrite the optimization problem. We are given an initial estimate of the current model beta, and we want to optimize over W subject to an equality norm constraint. Here, the linear constraint is actually a hyperplane. And obviously, the optimal solution will correspond to the tangent point of this hyperplane to the level set of the objective functions. Luckily, we have a closed form solution here. In order to compute WD, we will use the absolute value of each beta d and compute its power, and then we rescale the whole vector to make it have a norm omega. So this formula actually translates a current model beta to a regularization structure W, which is quite intuitive. Basically, it states that in order to compute a regularization structure W, we need to reassign the global energy omega to different dimensions of beta, subject to power modulation according to their relative importance. This naturally leads to iterative procedures. We can start from a current estimate beta, and then we compute W, and then we can determine the adaptive regularization W to the power of negative gamma, and then we can perform adaptive lasso to obtain the model coefficients in the next round. So this iterative updates between the model and the regularization is actually a self-ameliorating process that drives the system to a desired state. For example, for those features with large entries in the current iteration, the corresponding regularization will be very weak, and the corresponding model coefficient will be very large in the next round. On the contrary, irrelevant features will keep being penalized very aggressively in the following iterations. Here, a very important problem is how do we choose the omega, because obviously it affects the optimal solutions. A key challenge here is that our optimization problem is non-convex. That means iterations might quickly get trapped into local optima. In other words, useful features in the beginning of the iterations might still be the relevant ones at the end of iteration. So in order to solve this problem, we need to borrow ideas from annealing. Annealing is a very popular heat treatment technique in material science. The basic idea is to heat a material to a high temperature and maintain this temperature for some time and gradually cools down the material. During this cooling process, the physical or chemical properties of the material can be greatly improved. For example, the inner stress of the material will be released, and the structures of the material will be more homogeneous through a recrystallization process. So next, we'll see how do we borrow this idea into our framework. Remind that the system status beta is actually affected by two competing terms. First is the model fitting, and the second is the regularization with a norm constraint. Here, the parameter omega makes it very convenient for us to interfere with the status of the model globally. That means by choosing a large omega, we will have a high temperature and dense model, and by using a small omega, we will have low temperature and a sparse model. With this in mind, we propose to anneal our system as follows. We'll start from a very non-informative W, for example, a vector of all ones, subject to a norm constraint. And then we compute adaptive lasso, we obtain the model, we translate the model to regularization again, and then we keep iterating until convergence. Remind that the iterations here are subject to a equality norm constraint. That is, the strength of regularization is controlled by omega. So in the beginning, we will use a very high temperature. That is, system will be very dense. And when the iteration converges, we will use this converged solution to initiate a next phase of iterations. But at this stage, we will slightly reduce the temperature. And when this iteration converges, and we will start the next round of iteration by using an even lower temperature. By doing this, the system goes through a series of self-adjusting microstages in which the regularization structure W is updated dynamically. So in order to have more intuition on this annealed sparsity, we will look into a detailed example. Here, we simulated a linear regression with 100 features. Among them, 10 features are relevant features with non-zero beta coefficients and are marked by the colors. And the rest 90 features are irrelevant and marked by the dashed gray lines. So as we can see in the beginning, when the system is very dense, all the features have the freedom to compete with each other. That means the energy of the systems are distributed more or less uniformly across all the features. When we anneal the system began to shrink. However, unlike the standard lasso, which tries to simultaneously shrink all the features, here, only the irrelevant features tends to be shrinked. And in contrast, the relevant features actually grow in their magnitude. So this discriminative shrinking, which obviously should be attributed to our annealing procedure, is extremely helpful in choosing the right model and selecting the right subset of features. And when we keep iterating, we can see that, it goes too fast. Let's go back. And at a certain point, we can see that all the irrelevant features actually shrinks to 0. And the relevant features still keep their magnitude, and they will keep being dominant until an optimal shrinking point. And this optimal shrinking point can only be selected by using cross-validation. Okay. So now we can draw a global analogy between annealing and our annealed adaptive shrinking. In annealing, by gradually reducing the temperature, we can improve the properties of the material. And in our approach, by gradually tuning the temperature parameter omega, the quality of the model or feature selection can be gradually improved, and the optimal shrinking will happen at a certain value of omega, which will be chosen by cross-validation. And a very important thing I want to emphasize here is that the dynamic solution path of our approach differs significantly with that of the standard lasso. This is because in standard lasso, theoretically, the solution path for each lambda can be computed independent of each other. However, in our approach, the solution path under a certain temperature omega will have to be computed based on the system status of these previous iterations. Actually, it's exactly because that system keeps shrinking and keeps translating the system status to the regularization structures that we arrive at this improved performance. OK, our approach can also be extended very conveniently to multitask problems. OK, now let's report some experimental results. We compare with a number of different approaches, such as the LASSO and adaptive LASSO. Here, we also chose adaptive LASSO 2, which basically determined a regularization weight by the inverse of a marginal regression from each feature to the target values. And we also compare with multitask LASSO, which uses a mixed norm regularization that enforces very strict group-wide sparsity. And the reweighted LASSO is an iterative version of adaptive LASSO. For all these approaches, when we want to work on multitask problems, we will average the regularization coefficient across different tasks. Here we have generated some simulated data as well as eQTL analysis in human cancer. And we use some very standard metrics to evaluate the performance of different methods. So the first one is a single task regression. Here we have a linear regression with 100 samples and 256 features. Among them, only 20 are useful ones. And we have chosen a noise level sigma equal to 1. And here we have plotted the curve of specificity versus the true positive rate. The starting point of this curve on the left top is sparsest solutions. And when the curve gradually goes down to the right bottom, actually the solution becomes denser and denser. As we can see, in terms of both feature selection, that is the left curve, and in terms of model prediction, that is the mean squared error in the right figure, both demonstrate that our approach is superior to the competing methods. Our second task is multitask regression. Here we have chosen a 5-task problem with 100 features, 40 samples. And among these tasks, only 20 features are relevant across the different tasks. Here we have strictly followed the group-wide sparsity pattern. That is, the model coefficients in each row are either all zeros or all non-zeros. Again, we can see that in terms of the feature selection, the performance of our approach, which is the red line, significantly outperform others. We also violate this strict group-wide sparsity assumptions, and by randomly picking one non-zero rows in the model coefficient matrix and set it to 0. In this case, the mixed norm regularization obviously has been violated, and we can see that adaptive LASSO is much more flexible in imposing this group-wide sparsity with certain violations. We also give some case study on how should we select the parameters. The first one is omega. We have to start from a very large omega to guarantee that system is hot enough and dense enough. So here we can see that typically we need a high temperature for the algorithms to perform well. Another parameter is the annealing factor delta. That means between each stages, we will gradually reduce the temperature by delta. Of course, we need a very smooth annealing process instead of a quick one, because in the latter case, the system might quickly get trapped into a local solution. Both these figures are quite intuitive. So our last experiment is the bioinformatics application on the on eQTL analysis. Basically, it is a problem of studying how the DNA variants at certain locations in the genome can affect the gene expression in that specific locus. To be more explicit, we have actually got our data from the CCLE project. We have the design matrix X is the DNA copy number, and the target Y is the messenger RNA expression levels. So we have chosen 6 target genes from the P53, which is a well-known tumor suppressor genes, and 6 genes will correspond to 6 tasks. Here, first we have the prediction error of the mRNA expression level. We can see that the first 2 methods, LASSO and adaptive LASSO, LASSO and multitask LASSO, give the worst performance. One of them totally ignores the group-wide sparsity, and the other enforces very strict group-wide sparsity. Adaptive lasso and its variants gives better results, which demonstrate adaptive lasso is more flexible in imposing these multitask structures. And for our approach, the error is the lowest, and is about 15% lower than the second best, which is the adaptive lasso. In order to explore whether the identified genes from each task is making biological sense, we follow the standard procedures of gene enrichment analysis, and by using the software and a canonical pathway data set. Because of the time limit, I will skip the details, but we can conclude that the features identified by our approach making biological sense, and actually it's much more than other approaches in terms of number of selected pathways. Okay. To conclude, in this work we have proposed a annealed sparsity that simultaneously improves both the model and the regularization. It can improve the quality of the feature selections and prediction errors, and it's also quite useful in multitask learning. And in the future, we will study how to compute the dynamic solution paths more effectively and in a computationally more efficient manner. And we're also considering incorporating the task level constraint in our formulation. Okay. And thank you for your time, and any problem are welcome.
Thank you for your talk. I might have missed this, but do you have any figures or something to say about how many iterations do I need for the new adaptive algorithm compared to, say, regular lasso, adaptive lasso?
Okay. For our approach, typically we need, depending on the choice of the shrinking factor on the temperatures, we will choose it as typically as 0.8 in our experiments. And we observe that typically we need around 50 to 100 iterations to converge.
All right, thank you.
Some more questions? So can you give an intuitive interpretation that why doing annealing? Because in my understanding, I think annealing is somehow you use different regularization parameters for different features in LASSO. And
okay.
What's the intuition that?
Okay. Our intuition is like we want to use the model itself to improve the choice of the regularization structures. However, due to the non-convexity of the problem, it's very hard to choose a global optimal W in one shot. Therefore, we think the iterative shrinking might be helpful in gradually improving the quality of the regularizer, and starting from dense solutions in which we impose the least prior knowledge or assumption, the system actually gradually evolve and improve itself. So we believe intuitively this is a useful scheme.
Thank you. So any other questions? Oh, so if there's no questions, let's thank the speaker again.